The James Webb Space Telescope has uncovered something truly remarkable: beams of light that look like they are radiating from an urban center, shining from a location light years away. This discovery has sparked renewed interest in the potential existence of extraterrestrial life. The telescope directed its focus towards Proxima Centauri b, the nearest exoplanet to our solar system, and noticed strange, brilliant flashes of light. These signals could be from an alien race or civilization. Stay tuned for more developments. For years, both scientists and the general public have been captivated by the concept of life beyond Earth. Any evidence hinting at the presence of life in outer space has been met with great enthusiasm. But a pivotal moment came when the James Webb Space Telescope presented clear evidence suggesting the existence of life somewhere in the cosmos. While scanning the depths of space, this powerful telescope discovered something extraordinary on an exoplanet located far away. It detected lights that resembled those from extraterrestrial cities, igniting the possibility that an alien metropolis might exist on that distant planet. This concept has produced significant excitement and curiosity within the scientific community, as it could be the breakthrough they have long anticipated. It hints at the presence of intelligent beings operating civilizations in ways we are only beginning to explore. Looking at these lights, resembling those of a large city at a distance of 4 light-years away, NASA engineers are astonished and wonder just how long they might have been visible in space, waiting for our technology to advance to the point where we could detect them. David Kipping, an astronomer at Columbia University, has written about the planet where these lights were discovered as particularly intricate. Unlike the majority of rocky planets, which absorb sunlight and emit energy as infrared radiation, this exoplanet behaves differently due to its unique relationship with its host star, Proxima Centauri. This discovery, made by the James Webb Space Telescope, underscores the telescope's critical role. Its ability to capture infrared wavelengths was essential in identifying the unusual behavior of Proxima Centauri b, which is crucial for understanding the planet's atmospheric conditions. Researchers are planning to continue using the telescope to study the atmosphere of this planet in more detail, with hopes of investigating whether it might be habitable. The James Webb Space Telescope has a high sensitivity to infrared light, enabling it to observe what happens on Proxima Centauri b even during the night. Many telescopes struggle to detect faint light in the vast darkness of space, but where the Webb telescope shines is in picking up even the faintest glimmers. This makes it an ideal tool to confirm if the alleged city lights on the dark side of Proxima b are indeed real. The telescope can detect artificial light in space, as long as it fits within a very specific frequency range, much narrower than the light emitted by regular stars. Proxima Centauri b has a dynamic interaction with its star, which heavily influences its environment. Like many planets that orbit stars, it captures intense energy from Proxima Centauri. As the planet revolves around the star, it goes through cycles of day and night much like Earth. The planet experiences scorching heat during the day and cooler temperatures at night. The range of temperatures on Proxima Centauri b is vast, primarily due to its composition. For example, if the planet has an atmosphere, the temperature difference between day and night would be extreme, hot on one side and frigid on the other. This dramatic thermal fluctuation is a key area of interest for astronomers, as it provides valuable clues about Proxima Centauri b's atmospheric makeup. The James Webb Space Telescope, with its ability to image in the infrared spectrum, can effectively examine the planet's thermal emissions, offering insights into its atmospheric properties. Interestingly, the orbit of the James Webb Space Telescope around Earth coincides with the orbital period of Proxima Centauri b, which enables scientists to make detailed observations of its daylight cycles every 11.2 Earth days. If Proxima Centauri b has an atmosphere, the next step will be to analyze its chemical composition to determine if it could enable life. Detection features like oxygen, water vapor, and methane would suggest the planet's potential to harbor life. This would involve studying the light passing through the planet's atmosphere, a complex process. While the James Webb Space Telescope is excellent for describing the atmospheres of planets, it is primarily designed for other tasks. Its expertise lies in analyzing the concentrations of water vapor, carbon dioxide, and methane, but it is less adept at detecting free oxygen, a crucial sign of life. Nonetheless, the telescope can search for other key indicators like ozone, which signals a healthy atmosphere. As scientists examine the data gathered from the James Webb Space Telescope, the hunt for distant worlds continues. The search is bringing us ever closer to answering the question of whether we are alone in the universe. It's important to note that the James Webb Space Telescope can only observe a limited number of exoplanets closest to Earth. For more detailed studies of planetary atmospheres, astronomers will rely on ground-based observatories like the Extremely Large Telescope, ELT. which is set to begin operations in 2027. The ELT is designed to offer a deeper look at the atmospheric structures of far-off exoplanets, providing clearer and more detailed data on their potential to support life. Scientists are eagerly awaiting the launch of future space telescopes like the ELT. In the meantime, the James Webb Space Telescope remains an invaluable tool for exploring distant exoplanets. Despite its limitations, the Webb telescope continues to offer critical information that may change our understanding of what exists beyond our solar system. Researchers have ambitious plans for future space telescopes. They aim to develop technologies that reduce starlight interference, allowing for better observation of the surrounding planets, similar to using your hand to block the sun in order to see more clearly. These upcoming telescopes will be able to focus on the faint light reflected by exoplanets, making it easier to analyze their atmospheres and assess whether they might be capable of supporting life. However, this task is far from simple. Stars are incredibly bright, often vastly outshining the planets around them. This brightness makes it difficult to detect the faint light that planets reflect, which is essential for studying their characteristics. To address this challenge, scientists are working on several innovative techniques. One such method involves the use of coronagraphs. These devices are placed inside telescopes to block out starlight while letting the light from the planet pass through. By carefully shaping the light waves, coronagraphs can significantly reduce the brightness from the star, making it easier to detect the dim light from exoplanets. As artificial lighting or atmospheric biosignatures had remained elusive. But the recent observations from the James Webb Space Telescope, JWST, have changed the conversation entirely. The intensity and regularity of the light patterns observed suggest something more structured than natural phenomena. While cosmic occurrences like auroras or volcanic eruptions could, in theory, produce light, they do not typically emit the kind of organized, grid-like illumination that resembles urban sprawl, a trait more commonly associated with intelligent design. This discovery has reignited debates within the astrobiology community. Some scientists urge caution, emphasizing the importance of ruling out all natural explanations before making extraordinary claims. Others, however, are beginning to openly speculate about the possibility that we may be witnessing the distant glow of an alien civilization, the first glimmer of intelligent life outside Earth. Proxima Centauri B's location in the habitable zone, its rocky composition, and now the possible detection of artificial light all point to the planet as a top candidate for life. If future observations confirm the presence of an atmosphere containing gases like methane and carbon dioxide in unusual ratios, or trace amounts of industrial pollutants like nitrogen dioxide, unlikely to exist in such abundance without artificial processes, the implications would be staggering. NASA and ESA, European Space Agency, are already planning targeted follow-up missions. These include long-term monitoring campaigns that will observe Proxima Centauri b through different phases of its orbit. Scientists hope to determine whether the light pulses remain constant or change over time, which could indicate technological activity, such as fluctuations in city lighting or energy usage. Beyond Proxima b, astronomers are identifying similar Earth-like exoplanets that may also host life. Worlds orbiting stars like TRAPPIST-1, Tau Ceti, and LHS 1140 are being prioritized for follow-up analysis using the JWST and, eventually, the Extremely Large Telescope, ELT. These instruments, working in tandem, could provide a holistic picture, not just of potential life, but of how life might evolve and adapt in environments vastly different from our own. This surge in extraterrestrial research is also catalyzing developments in adjacent fields, philosophy, theology, ethics, and even international policy. If humanity confirms the existence of intelligent life, how do we respond? Do we attempt contact? If so, how? And who represents Earth? These are no longer hypothetical questions reserved for science fiction. They are becoming urgent topics of real-world discussions. The road ahead is full of uncertainty, but also promise. We may still be years away from irrefutable proof of alien life, but never before have we stood so close to the possibility. The James Webb Space Telescope, with its unparalleled sensitivity and reach, has ushered us into a new era, one where the question "Are we alone?" is no longer rhetorical, but scientific. And if those SETI-like lights flickering across the void are anything to go by, we may not be alone after all. As artificial light or signs of civilization was a dream for many scientists, the fact that such light has been detected by the Webb telescope only enhances the hope that one day we may contact other intelligent life forms in the universe. This kind of discovery fuels both scientific curiosity and public imagination, inspiring new generations to think beyond the confines of Earth. As the James Webb Space Telescope continues its observations, It's not just looking for synthetic lights but also focusing on planet atmospheres, their chemical compositions, and how these things might help life. The search for biosignatures like methane or carbon dioxide in the right concentrations is vital for understanding whether these planets have the ideal circumstances for life. The Webb telescope has the ability to look at these atmospheric components in a way no other telescope has been able to, shedding light on the potential of distant worlds to support life. Similar to one of the most fascinating creatures on Earth, aspects of Proxima Centauri B include its location within the habitable zone of its star, where the right conditions might exist for liquid water to exist on its surface. The habitable zone is the region around a star where temperatures are just right, not too hot and not too cold, for liquid water to form. This is considered a critical factor in determining whether a planet could harbor life. Water is essential for life as we know it, making the discovery of an exoplanet within a star's habitable zone a key target for future missions. In addition to finding life-supporting planets, future space telescopes will also be focusing on the complex relationship between exoplanets and their stars. Some planets, like Tauri B and Proxima Centauri B, are tidally locked, meaning one side always faces the star while the other side remains in darkness. This can create extreme temperature differences between the two sides of the planet, which would affect the planet's climate and its potential to support life. Understanding these conditions is crucial for astronomers in their evaluation of the likelihood of habitable environments on exoplanets. The development of technologies that can block out the bright light from stars is another major step forward in space exploration. Without the ability to block out starlight, it would almost certainly be impossible to observe the faint glimmers of light from distant planets. The coronagraph and starshade technologies cited earlier are excellent examples of how scientists are overcoming these challenges. By blocking out the uncontrollable brightness of a star, these tools will enable telescopes to detect the faint light reflected by planets, which could reveal crucial details about their surfaces, climates, and potential for life. Another exciting development in this field is the concept of direct imaging of exoplanets with the help of advanced adaptive optics and starlight blocking technologies. According to astronomers, these technologies can take high-resolution pictures of planets as they orbit their stars. These images would not only provide more detailed information about the planet's composition and atmosphere but could also offer a closer look at the planet's surface features, such as oceans, continents, or weather patterns. This type of imaging would represent a giant leap in our ability to study exoplanets and make informed decisions regarding their potential to support life. As we continue to explore the universe and search for answers about the existence of life beyond Earth, the role of the James Webb Space Telescope and future missions will be indispensable. The telescope's ability to detect faint signals from distant planets, analyze their atmospheres, and examine their habitability potential is transforming our understanding of the cosmos. With advancements in technology and an ever-growing body of research, we are on the brink of making discoveries that could reshape our knowledge of life in the universe. These breakthroughs not only deepen our scientific knowledge but also challenge our philosophical and cultural perspectives about our place in the cosmos. The possibility of discovering life beyond Earth raises profound questions about the uniqueness of humanity, the diversity of life forms, and the potential for communication with extraterrestrial civilizations. Moreover, the technological innovations developed for these missions often have broader applications, driving progress in fields such as imaging, materials science, and data processing. As telescopes become more powerful and our methods more sophisticated, the scope of exploration widens, from detecting distant exoplanets to probing the atmospheres of moons within our own solar system. International collaboration plays a vital role in these endeavors. Sharing data, expertise, and resources accelerates discovery and ensures that the quest to understand the universe remains a collective human effort, transcending borders and cultures. Looking ahead, the integration of artificial intelligence and machine learning promises to enhance the analysis of vast datasets collected by these space observatories, helping scientists identify subtle patterns and anomalies that might otherwise go unnoticed. In the coming decades, as new telescopes are launched and ground-based observatories are upgraded, the synergy between observational astronomy, theoretical modeling, and laboratory experiments will create unprecedented opportunities to unlock the secrets of life's origins and its potential distribution across the universe. Ultimately, the journey to find life beyond Earth is not just about answering a scientific question. It is about expanding humanity's horizons, inspiring wonder, and forging a deeper connection with the cosmos that surrounds us.